indivisible.
Okay, sorry. So Dalton assumed that the atom is not divisible. It cannot be divided any further. But J.J. Thomson discovered protons and electrons. Okay, and J.J. Thomson now decided, or proposed rather, that the uh, atom is neutral, just like Dalton proposed, except that in the atom, there are negatively charged electrons hovering around a positively charged system. Okay? And he came up with what we call the pudding model. The pudding model. Okay, the pudding model is just like the gari you put in your gari, the granite you put in your gari. You understand? Or the sugar you put in your gari. You know, when you put the sugar is the electrons. The sugar will just go everywhere, okay? But the gari itself is positively charged. That's the way he described it. The gari itself is positively charged. Then on adding sugar, the electrons, which is the sugar now, will now spread, will just be going about freely inside the gari. So that was Thomson's proposal, okay? Then another person, Rutherford, did the gold foil experiment by bombarding a thin sheet of gold with alpha particles. So with the alpha particles scattering, I'm just summarizing, with the alpha particles scattering, he proposed that, well, that J.J. Thomson's model is correct that the atom is neutral. However, that the positively charged particles are not scattered all around the atom. The positively charged particles are at the nucleus. And that is where the heavy center is. That's where the main weight of the atom is. So he proposed that the atom has a heavy center, a dense center that is positively charged. Okay, so all the positive charge is at the center, which he called the nucleus. Then the electrons are just hovering about randomly, like smoke. They are just hovering about randomly around the atom. Then from there, another modification came. Niels Bohr came with his own modification. Niels Bohr said, yes, that the nucleus is truly positive, right? The nucleus is truly positive. It is at the center of the atom, but the electrons are not just moving about randomly, that the electrons are moving around in orbits, okay? They are moving around the nucleus in orbits, which we now call shells, okay? Which we now call shells, all right? So that is up to this level of your study. This is the much you are expected to be able to explain the orbital diagram of the atom. But furthermore, Schrödinger did another further work, and Schrödinger came up with the theory that electrons are not exactly revolving around an orbit. That orbit is actually like a cloud or a region where there is high possibility of finding electrons. Okay, so he assumed that electrons are just, they revolve around the nucleus. That's correct. But they do not revolve particularly on a certain line. Okay, they do not revolve on a certain line. So his proposal looked more like, let me doodle this, look more like, okay, this is the nucleus, for instance. And if the electrons are revolving around the nucleus, his proposal is that the electrons are not just on one line, they are revolving around a region. Don't mind that circle that went too close to the nucleus. They are revolving around a region like this. Okay? So that shell or that orbital is the region where there's high possibility of finding electrons. Are we together? So we see how the atomic model modified from this to this to this to this, and finally to the Schrödinger's electron cloud model. That's what we call it, electron cloud model. This is the orbital model. All right, then the electron cloud model. Now that said, what we are looking at today is a very close, we are looking at the electron even closely. As a matter of fact, we are going to mentally go into the atom to see what is going on inside the atom. So I hope your mental eyes are open and ready to look at what goes on inside the atom. But let's look at our learning objectives. What are you supposed to have, or the package you should have at the end of this class? You should be able to outline the major atomic models from Dalton to Schrodinger, just like I have stated. You should be able to outline the major atomic models from Dalton to Schrodinger. Then you should be able to distinguish shells, subshells, and orbitals. Now you are promoted from the shell 1, shell 2, shell 3. We are entering what we call subshells. Then inside the subshells, we are going to be looking at another what's name we call orbitals. Inside the subshells, there are orbitals. Okay, these are the things we are going to be looking at today. All right, and I believe that before we close for today, you would have picked up all these. Then you should be able to state and apply the Aufbau principle, the Pauli exclusion principle, and the Hund's rule of maximum multiplicity. These are three rules that actually guide how electrons are arranged in an atom. Okay, how electrons go into an atom. Then describe these shapes and capacities of S and P orbitals, shape and capacity. Then you should be able to use the 4 quantum numbers to describe an electron. We are going to do quantum numbers hopefully today. I might have to rush this if we do that. Okay, quantum numbers to describe electrons. Then we should also be able to write electron configurations and explain the hydrogen emission spectrum. This is quite a load, but we are going to do the much we can do today without leaving any confusion in your head. And in our next class, we are going to finish up. There is no need to rush anything. Your understanding is far more superior than finishing. All right. So let's look at the first concept here, the atom itself. The atom itself. So atoms are extremely small particles that make up elements. Now, scientists cannot see an atom. You need to understand that. Scientists cannot see an atom directly with the naked eye, so they build models from experimental evidence. Each newer model explained observations that the previous one could not explain. So we are not entirely saying that the first model is totally wrong. We are just modifying 1 or 2 things from previous models. And I'm hoping that maybe one of my students in this class, your own model is going to come up here. Your own model is going to come up here. All right. If that is you, say I, or mute yourself and say I. Do I have students in this class? I'm not hearing I. Does that mean you have no plans of If that is you, if your own model, you are going to work, okay. Most of you don't even like chemistry. That is what I've noticed. You are just doing it because you must do it a while. You must like chemistry. Chemistry is in fact, chemistry is the most interesting subject I know. All right, very, very interesting subject. You see how we explain things that cannot be seen with the eyes. We explain things that cannot be seen with the eyes. Okay? In fact, it is a spiritual science because most of the things we talk about, you cannot see them. You only see their manifestation. We talk about electrons, we talk about protons, we talk about atoms. You don't see no atom. You don't see any molecule. Okay? But if you want to doubt the existence of electrons, just go and touch a naked wire. You will understand that electrons are there. Are we together? Nobody will explain further what electrons can do. So electrons exist. We know they exist. We have evidence to prove them, but we have never seen them. Isn't that powerful? So these are the, like I explained initially, these are the various modifications of the atomic model. Okay? Modifications of the atomic model. Now I'm going to call your names one after the other to you're going to read these, what you can see on the screen. Okay. Chukwubuike Mmaduagwu. Chukwubuike Mmaduagwu. Unmute yourself. Chukwubuike Mmaduagwu. Unmute yourself. Very good. Chukwubuike Mmaduagwu. I want you to read me John Dalton 1803, his main idea and why it mattered and his limitation. John Dalton, 1803. Go on.
Matter is made of tiny, indivisible, solid atoms.
Mm-hmm.
Atoms of an element are alike.
Okay. So why does this proposal matter? Read.
Explain laws of chemical combinations. It could not account for electrons, isotopes, or subatomic particles.
Subatomic particles. So you see, most of these proposals, they had their small issues. So now I want Eko Kamsi. Eko Kamsi, unmute yourself and read J.J. Thomson.
J.J. Thomson, 1897.
Good.
After discovering the electron, he proposed electrons embedded in a positive sphere, that is plum pudding.
Plum pudding. Okay. Why does it matter?
Show that atoms are divisible. It did not explain alpha particle scattering.
Alpha particle scattering. Very good. Very good. So, Onwuka Carlos Samuel, your turn now. Unmute yourself and let's hear. You are our Ernest Rutherford today. You are Ernest Rutherford. Go on.
Goldfield experiment. Most of an atom is empty space. A small dense positive nucleus contains most mass.
Okay.
Why it mattered? It explained large angle scattering. It did not explain stable electron energies.
Very good. Very good. Very good. His proposal did not explain stable electron energies. You understand? The energy of an electron is within an atom is somewhat stable. So if the electron keeps moving the way he was proposing, moving up and down the way it was proposing, you know that the energy of the electron close to the nucleus and its energy far from the nucleus will not be the same. So his proposal did not explain that. That was from Onwuka Carlos Samuel, isn't it? Opara Brian, you are our Niels Bohr today. Read Niels Bohr. Unmute yourself.
Niels Bohr, 1913. Electrons occupy fixed energy levels and gain or lose definite packets of energy. Why it mattered? Explain the hydrogen line spectrum well, but not multi-electron atoms fully.
Very good. Very good. So Niels' model of the atom explained hydrogen line spectrum. That's the emission spectrum we are going to discuss today. He was able to explain it for only an atom with one electron. But when the atom now has multiple electrons, his theory started having issues. His proposal started having issues. Then Udebunu Chinyere, where are you? Udebunu Chinyere, you are our Scrodinger today. Where are you? Unmute yourself. Oh, is she gone? Okay, Victory, you are our Scrodinger today.
Electrons have wave-like behavior. Electrons have wave-like behavior. An orbital is a region of high probability of finding an electron.
Okay.
Why it mattered? The modern quantum mechanical model, it does not give a simple circular path for an electron.
Good. Now, some of these things can be very, very complicated when you are talking about it, especially when you are showing it in 2 dimensions. You miss the opportunity to be our Erwin Schrodinger today. But maybe we'll give you another name down there. As we proceed down, we'll give you another name. Schrodinger is a very powerful name for a woman. Okay, so now you see from this table, when you study it later on, you see that there was a problem with each atomic model. Even the Schrodinger's model still has some small issue there. It does not give a simple circular path for an electron. Okay, so I don't want to bore you with the complicated depth of this theory. We are going to just move from shells to orbitals. Okay, we move from shells to subshells. Then from subshells, we move to orbitals. Now, these are terms you must understand, because often students will be describing an atom and they'll be calling an atom electron, or they'll be describing an electron and they'll be calling the electron atom. You know, these are mix-ups that are avoidable, and we want our students to be able to describe the atom confidently and know exactly which part of the atom they are referring to at every point in time. So, let's look at this level. Okay, let me read from here. The modern model retains the useful idea that electron energy is quantized. That means electrons are, they orbit around the nucleus in packets of energy, okay? They don't flow from one energy level to the other. There is a jump, okay? They have a quantized energy level. So electrons can have only certain allowed energies. However, it replaces Bohr's circular path with orbitals. So instead of just spheres, instead of just those what do we call it? Shells. Instead of those shells, we now have what we call orbitals, and we are going to understand what the orbitals are today. Electrons are arranged in levels that become progressively more detailed. Electrons are arranged in levels that become progressively more detailed. Now, let's look at shell and principal energy level. What does shell mean? From this table, you can see that shell generally is a distance, an energy region around the nucleus. I need you to pay attention to that. Okay? It's a distance from the nucleus, just an energy region from the nucleus. So this is the nucleus here. This is the nucleus, and this is a shell. And this is a shell. Okay? Now let me make it let me correct that. This is a shell. I'm supposed to draw it as one circle. So this is the shell as proposed by Niels Bohr. All right? Now, maximum number of electrons a shell can carry. Please take note of this. Everybody write it down. The maximum number of electrons a shell can carry. I'll still send you this note too, but I know what I'm saying. You should note this down. The maximum number of electrons a shell can carry is given as 2n squared, where n is the shell number. See where you pick your n from. So I want to illustrate the n here. So this is the first shell. This is the K shell, shell 1. Okay, so n here is 1. Sorry, let me do that properly. So n here is 1. Then for the second shell, like this, n here is 2. For the third shell, like this, n here is 3. Oh, okay, sorry. Let me remove this. N here is 3. Then 4, 5, 6, and so on and so forth. Are we together? The maximum number of electrons a shell can carry is given as 2n squared. Now, let's move to subshells. Let's move to subshells, and I want you to understand this way. In very simple terms, a subshell as the name implies, is an energy level within a shell. An energy level within a shell. So let's say we want to expand this shell now to look bigger. We want to make it look bigger. Let's say this is the shell that moved around. This is the thickness of the shell. Please, everybody stay with me. This is the thickness of the shell. Okay? This shell 3, for instance. Now, what we mean by orbitals is that when you come inside the shell, you have the lowest level, which is the s orbital within that shell. Then you will have another level, let me use a different color, pink, which is the p orbital, still within that shell, within that shell 3. Then we'll now finally we'll have another level. Can you see it? Different colors represent different subshells within shell 3. I want to repeat. Each color represents different subshells within the same shell 3. So the shell is third shell. But inside the shell, that's why I said you have to get ready your mental eyes, because we are going inside the atom now. All right? Inside the shell, there are subshells, there are sub-energy levels. We call them subshells or sub-energy levels. And these sub-energy levels, they have names. Okay? They have, will I say notations? They have notations that we use to identify them. We have the S, you can see them here. We have S, we have P, we have D, and we have F. We have S, we have P, we have D, and we have F. Now, that doesn't mean that every shell has S, P, D, and F. For instance, this first shell, this shell 1 has only S. It does not have P, it does not have D, it does not have F. Okay? When we now come to shell 2 is bigger. So shell 2 has S subshell, and it also has P subshell, but it does not have the D and the F subshells. Then when we move to the third shell, the third shell now has the S, it has the P, and it has the D subshells. I don't know if you notice something, that the bigger the shells are, the more the number of subshells. So the bigger the shells are, the more the number of subshells. So who can tell me the subshells that will be on the fourth shell? Unmute yourself.
SPDF.
Sorry, say it again.
SPDF.
Very good, very good. The fourth shell now is going to have S, P, D, F. And these are the 4 subshells that are readily in existence based on the atoms that have been discovered so far. Are we together? Are we together?
Yes, sir.
Good. Now, let's go deeper. Okay, Kamsi, go on. Quick, ask your questions real quick.
What if enters fifth shell?
The fifth shell will also have SPDF. The sixth shell will also have SPDF. So for now, there's not been an atom. There's no existing, or not existing, let me not use the word existing. There's no discovered atom that has a subshell outside SPDF for now. For now. Okay? Maybe you'll be the one to discover it tomorrow, but for now, there is none. All right? So, let's move from, remember, we moved from shell and we expanded to subshell. Isn't it? We moved from shell to subshell. Now, I want us to move from subshell to orbitals. These orbitals are also energy levels inside the subshells. Again, we are going to make it as simple as possible. We are not going to make it complicated, okay? Now, when you come into the S, for instance, let me assume this blue one is S. S has only one orbital, which we represent with just one box like this. Then P has 3 orbitals, which we represent with 3 boxes together like this. I'm sure you may have seen something like this before in your textbook, but you don't know what it means. Then the D is represented with 5 orbitals. 5 orbitals. 1, 2, 3, 4, 5 orbitals. Okay. Then the F, which is the biggest, where should I show F now? Let me bring F all the way to this side. F has 7 orbitals. So let me draw it here. 1, 2, 3, 4, 5, 6, 7. Now, let me label them again. Let me label them so you don't mix them up. We said S has only 1 orbital. P has 3 orbitals. That means P has 3 energy levels inside it. Then D has 5. Sorry. What I was supposed to be writing is the name of the. Okay, so we have P has 3. Okay, then D has 5, and this is F having 7. This is F having 7. So I hope you realize that we are now going deeper and deeper, isn't it?
Yes,
we are
sir.
going deeper and deeper into the atom. We have entered the atom. From atom, we went to the shells. From the shells, we have gone to subshells. We were not satisfied with subshells. We delved into each subshell to see how many orbitals are there. And we saw that the S orbital, the S has only 1 orbital. The P has 3 orbitals. The D has 5 orbitals, and the F has 7 orbitals. Now, listen attentively. If you go into every orbital can only take 2 electrons. That's the maximum number of electrons that an orbital can take is 2. Let me repeat it again. The maximum number of electrons an orbital can accommodate. An orbital is just one box like this. Just like this now. It's one orbital. Okay? And I said the maximum number of electrons it can take is what? 2. If 2 is the maximum number of electrons an orbital can take, how many electrons in total are in the S orbital? Unmute yourself. Okay, I think I should be asking this directly now. I'm going to pick your names and ask you. If I call your name, Adez Ozago. Is Adez supposed to be in this class? Adez, are you in SS2?
Yes, sir.
Okay, in my mind, I've promoted you to SS3. Oh, amen. You'll soon be in SS3. Okay, Adeze, I'm sure you were in class when I was explaining the number of electrons in each orbital. So I want you to tell me now, how many electrons are in the S orbitals?
2.
2. Very good. Because S has only 1 orbital, so it has 2 electrons. So we are going to write them like this. 1, 2. I'm sure you have seen something like this before. Now, Chukwubuike Mmaduagwu. Chukwubuike Mmaduagwu. How many electrons, in your opinion? Chibuike, unmute yourself. How many
6.
electrons in your very good? 6. 6.
Yes, sir.
Chinyere Udebunu. Very good. Chinyere Udebunu.
Sir.
How many electrons does the D subshell have?
10.
Beautiful. Beautiful. Yeah, I have plenty Albert Einsteins in this class. So are you sure we are not going to discover another modification for atom from this class? I'm very sure that if they give us the right tools, we may just discover extra modifications from what Schrodinger has done. Then let me ask Victory. Victory, how many electrons do we have in the F subshell?
14.
14. Very good. Very good. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Very good. That means everybody here now understood my explanations. So I'm going to clear this and we are going to move on. So we can see from here, the table presents to us the maximum number of electrons a shell can carry, then the maximum number of electrons each subshell can carry. You can see there 2, 6, 10, 14. They differ by 4, 4, 4, 4 because the number of orbitals differ by 2, 2. Okay, if you check that well, the number of orbitals differ by 2, 2. So the number of electrons differ by 4, 4. Then the maximum number of electrons an orbital can carry is now 2. I believe at this point, everybody in this class knows what a shell is, now understands what a subshell is, then goes into have gone with us mentally into the subshell to see what an orbital is. Is there anybody here in this class that is going to be confused about these 3 things, shell, subshell, and orbitals? If there is any, please raise up your hand before I continue. Is there anybody that feel that they might be confused about subshells and orbitals in this class? Anyone? Anybody? Okay. I believe it means everybody is now, this is now settled. I can assure you that a huge part of your problem has just been solved because many students do not know this difference. Okay, you just hear them saying there are 8 electrons in the orbital. Because there are 8 electrons in the orbital, I'm sure that tomorrow if you hear something like 8 electrons in the orbital, you will leave your mouth open in shock because you now know that an orbital cannot take more than 2 electrons, isn't it? Good. So now let's look at the shapes of the S and P orbitals. Shapes of the S and P orbitals. Now, this is just for illustration purpose, and like I said, it is somehow difficult to explain a 3-dimensional structure as complicated as this using 2-dimensional plane. But I will find a video. I'll find a video that is going to do justice to these 3-dimensional structures so that you see them very well and appreciate them. Okay. Now, first, write this down that the s orbital is spherical. The s orbital is spherical. This is the s orbital. It is spherical. It's just like ball. All right. It's not a circle. Circle is different from sphere. I hope you know that. Here is looking like a circle, but it's actually like ball, spherical. Okay, with its nucleus right there. So it's spherical around the nucleus. Each shell has one s orbital. Every shell has an s orbital. That means the first shell has an s orbital we call 1s. The second shell has an s orbital we call 2s. The third shell, 3s. The fourth shell, 4s. Up to, 4s, not 47. 4s, all the way down to 7s, because the largest atom we know or that have been discovered has 7 shells. All right, so that's it. And taking the p orbitals are 3. They have 3 equal energy orbitals named px, py, pz. Please remember, we said the p orbitals are 3. The p is a subshell. So this whole thing here, everything here, is drawing a particular orientation of 1p orbital. So the 3 of them are in 1p orbital, but one of them is x, one is y, and the other is z. Okay? One is on the y-axis, the other is on the x-axis, the other is on the z-axis, if you want to, if that makes it a little bit better. Okay? So this has a dumbbell shape. Okay? They have 2 lobes separated by a nodal plane through the nucleus. Now, to make this a little bit easier for you, okay? Write this down, that the p orbital has a dumbbell shape, like figure 8. Dumbbell shape. That's mostly what you are going to see in your textbooks. Okay? It has a dumbbell shape. Now here they are separated. They are separated because if they are brought together, it's going to look too complicated and difficult for you to understand. Okay? So P has 3 orbitals and it has a maximum of 6 electrons, and there are 3 orbitals in the P subshell, and there are maximum of 6 electrons in the p subshell. So we say it has dumbbell shape, dumb, D-U-M-B-B-E-L-L. You know dumbbell now, like for weightlifting, that small hand lifts, that's dumbbell shape. But when we draw it, if you look at it in your textbook, it will just look like figure 8. Okay, this diagram here is trying to give you a better picture of it, but I don't want you to get confused or get anything mixed up with information that you cannot actually absorb at this point. So it is very simple. S is spherical, P is what? Dumbbell. All right? P is dumbbell. As we progress, we are going to understand the structure of the S and P orbitals more. At your level, WAEC will not ask you the structure of any other orbital if not S and P, both WAEC, JAMB, and NACO. So quickly, without wasting time, I want us to look at the rules, the 3 rules for filling electrons into orbitals. There are 3 rules for filling electrons into orbitals. The first of the 3 rules is the Aufbau principle. The Aufbau principle. Chinyere, please unmute yourself and state this Aufbau principle. In a ground state atom, continue from there.
Electrons occupy the available orbitals of lowest energy first.
Very good.
The commonly used order is.
Very good. Very good. Now, for the Aufbau principle is just saying that electrons go into lower energy first. Okay? Remove that thing you wrote there. Electrons go into lower energy level first before moving to higher one. That means an electron will first go into the first shell. And when it goes into the first shell, it will go into the 1s, which is the lower energy of the first shell. That's the only subshell anyway, and the only orbital. Then when it comes to the second shell, electrons will fill the 2s first before filling the 2p. Electrons will fill the 2s first before filling the 2p. So when 2 electrons fill the 2p, the 2s, a third electron cannot enter the 2s. So the next electron will go into p. Are we together? So that is Aufbau's principle. And there is a chart that actually gives us this order. You may copy this order, but there is a chart like this. Let me see. Let me zoom this and give you this chart here. I want to give you the chart right here. Okay? The chart that you're going to use to, in fact, with this chart, you can write the electronic configuration of an element with atomic number 100. If you understand this chart very well, you can use it to write the electronic configuration of an atom, or an element rather, with atomic number 118. In fact, you can even write for 150 for an atom that is not, for an element that is not in existence yet. So this is the order. There is 1s, 2s, 2s, 3s, 4s, 5s, 6s, and of course down here there's 7s. Okay, then this is for the s. Now when we come for p, there is no 1p, so we'll go down to 2p, then we have 3p, okay, then we have 4p, 5p, 6p, 7p, and so on and so forth. Then there is no 3d. If you remember, there is no 2d. So d starts from 3. So we now have 3d, then 4d, then 5d, and so on and so forth. Then the f, there is no 3f. F starts from 4. So we now have 4f, then 5f. So we have 4f and 5f. All right. Now, this is how the shells go. You are going to follow this arrow like this. Down. 1s. Can you see that? 2s. 2p. After 2p, the arrow continues to 3s. After 3s, it curves right back. And does what? It hits 3p. After 3p, 4s. After 4s, it will curve right back all the way diagonally. 3d. Mute yourself. Adeze, mute yourself. Adeze, mute yourself if you can hear me. Thank you. So 3D. Okay. After the 3D, we have 4P. After the 4P, we have 5S. After the 5S, what do? We'll curve all the way back to what? 4D. After 4D, it is what? 5P. After 5P is what? 6S. After 6S, what do? We curve all the way back to what? 4D. 5D. After 5D, 6P. Like that. You keep following it diagonally. Now, what is the significance of this? You need to understand the significance of what I have just drawn here. The implication of this, what this shows you, according to Aufbau's principle, is that electrons will go into 4s orbital first. How many electrons can 4s take? Everybody unmute yourself, unless your background is noisy, then you can stay mute. But if your background is not noisy, unmute yourself briefly. I want us to do this together. Everybody. Everybody, unmute yourself. Now, how many electrons can the 4s can the 1s carry? Who can
One.
remind me?
Two.
2.
2.
2, very good. What about the 2s? How many can it carry?
6.
No,
Six.
2s.
4.
No, 2s. Good,
Two.
good. Now, this is what I wanted us to clarify. Okay, now pay attention so that you understand what 1s, 2s, 3s means. 1s means s orbital on the first shell. The s orbital that is in the first shell. 2s means the s orbital in the second shell. Now, will the s orbital in the second shell have more electrons? No, it is still s orbital. So it will have only one, it will only have 2 electrons, just like all the other s orbitals. So all the s will have 2. Are we together? I hope you all understand that. I said you should unmute yourself, so I thought I would be hearing you.
Yes, sir. Yes, sir.
Do you all understand that?
Yes, sir.
Yes, sir.
Good, good. Now, after 1s, we move to 2s. How many electrons does 2s carry?
2.
Very good. Very good. Now you understand it. Now, this is 2p, and 2p means the p set of orbitals in the second shell. So in the second shell, the p of the second shell, how many electrons can it carry?
6.
Who can remember?
6.
6, very good. And when we now come to 3s, how many can it carry?
2.
Very good. What about 3p now? We have advanced now. What about 3p? How many will it carry?
6.
6.
Sorry?
6.
It's still 6. As
9.
long as it is p. As long as it is p, it doesn't matter whether it's in shell 15 or shell 3. It is still 6 electrons. Then 4s will carry 2. 3d will carry how many? Who can tell me? 3d, how many?
10.
10.
Very
10.
good. Very good. Now, when you are asked to write electronic configuration, have you copied this? Because I want to clear it so that we'll go back to...
No.
Have you copied? You haven't. Do it immediately, or better still, I'll advise you to screenshot. I'll advise you to screenshot so that you won't rush it. Now, if you rush it, you might just be drawing one kind of snake like that. And I don't want you to draw spaghetti and say that is what I taught you as a Aufbau principle. You see the way it's looking now. Some people will just go and draw one Indomie like that, a plate of Indomie, and say that is what I taught them. Huh? So screenshots so that later on you calm down and draw it very well without any mistake. Because you could make a mistake now, and instead of 3P, you go and land on 3D. Before you know what's happening, you have gotten confused. Okay? So screenshots, next 10 seconds. 10 seconds, screenshots.
This is one screen I'm seeing this.
Sorry? I didn't get you. Somebody was talking. Hello? Or maybe he wasn't talking to me then. Okay, our time is up, so we are clearing this right now. So let's come back to this. Now, this thing you are seeing here, this sequence you are seeing here, is the order for filling electrons into orbitals. Where you will stop depends on how many electrons the atom has. Where you will stop, whether you stop on this first line or you stop here or you stop here, depends on how many electrons the atom has. So I want two people to give me, each person will give me an element from the first 20 or first 30 elements. so that we can write the electronic configuration so that you see how it is written.
Oxygen.
Oxygen. Okay, somebody has given us oxygen. So oxygen has a symbol O, isn't it? Pay attention, everybody. This is very important. Oxygen has symbol O. What's the atomic number of oxygen?
16.
Atomic number.
8.
Atomic number is 8. It is atomic mass that is 16. Okay? But for this electronic configuration, it is not the atomic mass we are using. What we are using is the what? Atomic number. Why are we using the atomic number? Pay attention so that you understand it. The atomic number is number of protons, isn't it?
Yes, sir.
Good. And the number of protons for an atom is equal to number of electrons. Is that correct?
Yes, sir.
Yes, sir.
Very good. That is why the atomic number gives us an idea of the number of electrons. But note that the number of proton is only equal to number of electrons for an atom. Once the atom gains electron or loses electron, the atomic number is not equal to number of electrons again. I hope you understand that.
Yes,
So
sir.
I am going to write the electronic configuration of oxygen here. Atomic number 8. Number of electrons 8. So out of these 8 electrons, I'll write 1s2. The S has taken, the first shell has taken 2 electrons. Are we together?
Yes, sir.
Now,
Yes,
when
sir.
we go to the second shell, how many electrons do we have left when we take away 2?
6.
We
have
have
how many?
6.
6 more.
6.
6.
Very good. You must remember how many is left. Now, when we go to 2s, how many are we going to give 2s?
4.
No, now.
2.
2s.
2.
2. It is still s. As long as it is s, it is still 2. So we are going to give 2s 2. How many electrons are left?
4.
4. Okay, now pay attention to this one. How many electrons can the 2p take?
6.
6. But how many electrons are left?
4.
4.
4. So we'll put all the 4 here. Why are we putting all the 4 here? That 2p can take 6. That means it can even take more than the remaining electrons we have. That means the electronic configuration of oxygen is 1s2. Let me write it here. 1s2, 2s2, and 2p4. Is that clear to everyone?
Yes, sir.
Yes, sir.
Yeah.
It's clear to everyone. Please, if you are
Yeah.
confused, please, this is the time to speak. Okay, so everyone understands this. Now, I want everybody to write oxygen like this, the way I wrote it here. Then write 8. Do not write that 16. Leave it out completely so that you don't get confused. Write 8 so that you always remember it is atomic number we are referring to. Okay? Then you write 8 protons equal to 8 electrons. Then you now write its electronic configuration. This electronic configuration is telling you how many electrons of oxygen are in each orbital and subshell. For now, for Aufbau's principle is each subshell. Are we together?
Yes, sir.
Yes, sir.
Good. Good. Then we are done with oxygen. I want a girl now to give me another element.
Carbon.
Carbon. Good. So carbon it is. Carbon symbol is C. What is its atomic number?
6.
6. So carbon has atomic number 6. So how many protons?
6.
6 protons. And is also equal to 6 electrons, isn't it?
Yes, sir.
Good. Now
Yes,
let's write the electronic configuration of carbon. What will it be? 1s.
2.
Good. 2s.
2.
2.
Good. 2p.
2.
Why not 2p6?
It does not have enough.
Very good, because we have only 2 more electrons. So just put in the 2 electrons there and we are done. So the electronic configuration of carbon stops here. So we'll write it here. Electronic configuration equal to 1s2, 2s2, and 2p2. Okay? So I believe everybody now understands the Aufbau principle.
Yes, sir.
Good.
Yes, sir.
Now, let's go to the second one, the Pauli exclusion principle. The Pauli exclusion principle. Now, you're going to listen attentively to this principle. An orbital can hold a maximum of 2 electrons, and the 2 electrons must have opposite spin. No 2 electrons in the same atom can have identical set of 4 quantum numbers. Can have identical sets of 4 quantum numbers. We are not going to discuss quantum numbers today. We are going to discuss quantum numbers in our next class. But you already have an idea of what the quantum number is. I wish we can finish everything today. You already have an idea. In our next class, make sure you read through these notes I'm going to give you before we discuss in our next class. Okay? Make sure you read through these notes very, very well. Is that clear? So that you will be well prepared to connect with the next thing. Now, what Pauli exclusion principle is saying is that there are no 2 electrons in an atom that will have exactly the same energy. No 2 electrons in an atom will have exactly the same energy. What does that mean? Now, listen to this. We have an atom like this. Let's say this is the nucleus, and this is the first shell, and this is the second shell, and this is the third shell. All right? So, Pauli exclusion principle is saying that in this atom, there are electrons everywhere, but none of them will be in the same shell. No 2 of them will be in the same shell, the same subshell, the same orbital, and have the same spin. Are we together now? I will explain that further because maybe when we do quantum numbers, you understand it better. You may have an electron here and you have another electron here. Are you with me now? These 2 electrons are on the same atom, but they are not on the same shell. Do you agree with me? Then, on that second shell, we have the s orbital and we have the p orbitals. Stay with me. I need you to understand this. On that second shell, if this is 2s and this is 2p, if you have an electron here, or 2 electrons here, and you have an electron here, the electron here in 2p and the electron in 2s, they are not the same. They don't have the same energy. The one in 2s and the one in 2p are not of the same energy because they are not in the same what? Subshell. Now, even if they are in the same subshell, look at that, this and this. These are 3 electrons in 2p. They are all in the second shell. They are all in the same subshell, which is p subshell. But if you look at it, you see that they are not in the same orbital. So they are still not having the same energy. Are we together? Then you may ask me, okay, what about these 2 electrons in 2s? What about these 2 now in 2s? Are they not having the same energy? Look at it very well. You will see that though they are in the same shell, second shell, the same subshell, which is S subshell, they are in the same orbital there of the S, but look at their spin. Their spins are opposite. One is in the clockwise direction, which we denote with plus half, and the other one is in the anti-clockwise spin, which we denote as minus half. So you see that no two atoms no two electrons rather in an atom, no two electrons in an atom will have the same, will be on the same shell, be on the same subshell, be on the same orbital, and have exactly the same spin. Let me show you something. Look at this electron I'm going to draw with red. Look at this. If you see anywhere that an orbital is described with two electrons spinning in the same direction like this, that is very, very wrong. It is not possible. If two electrons are going to be in the same shell, if two electrons are going to be in the same orbital, rather, they will spin in opposite direction. Their spins must be opposite. One will be plus half, the other one will be minus half. When we do the quantum numbers, you are going to understand the Pauli exclusion principle far better. Then let's look at the Hund's rule of maximum multiplicity. Hund's rule. What the Hund's rule is saying in simple English, because sometimes the problem some of our students have is the English, the grammar that is used to explain or to state some of these rules. In simple terms, Hund's rule is saying that if you come to a set of degenerate orbitals, electrons will enter singly. Now, degenerate is another big word. Degenerate simply means orbitals in the same subshell. Orbitals in the same subshell. So if this is 3p, these three orbitals are degenerate. They have equal energy, or approximately equal energy. Listen attentively. Hund's rule is saying that when you are now writing electronic configuration and you are putting electrons into orbitals, for carbon, for instance, you put one here and you put one here. Let's write the electronic configuration of carbon again. The electronic configuration of carbon is 1s2. Sorry, I need to write it in such a way that you will have clarity. Okay, I need you all to understand that. 1s2, that's for carbon, carbon 6. 1s2, 2s2, then 2p2, isn't it?
2.
Now,
Yes, sir.
the s has only one orbital, remember? So 2s is also 1. But the 2p is how many? 3.
3.
So this Hund's rule is saying that when you come to put electrons, this is how you put it. This is an orbital. 2 electrons, you put one like this, opposite spin. You come to shell 2. Sorry, there are 3. You come to shell 2, one like this, one like this. If you come to shell 3, you put 1, 1. One here, one here. What is the element after carbon? Real quick, fastest thinker after carbon.
Nitrogen.
Nitrogen. Somebody said it first, but the network betrayed the person. Very good. Nitrogen. Now, for nitrogen now, let me show you for nitrogen. Nitrogen is 7. So nitrogen's own will be like this: 1s2, 2s2, 2p what? 2p what? 3.
3.
So we'll go 1, 2, 3. You don't join 2 together when there is an empty orbital. Are we together? If there's an empty orbital, they will take 1, 1 first. Then what is the next element?
Oxygen.
oxygen. That's our oxygen there. So oxygen is 1s2, 2s2, and 2p what? 2p4, isn't it? Now, the rule for oxygen now, you see where Hund's rule is playing out. You go 1, 2, 3. Because you have filled all of them singly and you still have one electron, you can now start pairing. Are we together? You can now start pairing. Yes, so when we now go to fluorine, fluorine is after, what do we call it? Oxygen, isn't it? Fluorine will now have 1, 2, 3, 4, 5. The neon will now complete it. For noble gases, usually they will complete it. I hope you understand this. Do you understand this? Everybody? Anybody that is confused should say so. We are rounding up. Okay, so I want to assume that everybody got this. So, Hund's rule of maximum multiplicity. Okay, that's it illustrated there. So I used arrow up and arrow down. You see that the down one is with red, the up one is with green to show you the different orientations or spin of the electrons. You see the nitrogen, you see the oxygen electronic structure there. All right, so let's look at some worked examples. Okay, worked example one, we've already done this. We've already done these ones. Okay, so we are going to stop here for today. In our next class, we are going to look at the 4 quantum numbers: principal quantum number, angular quantum number, magnetic quantum number, and spin quantum number. This angular quantum number sometimes is called subsidiary or azimuthal quantum number. Subsidiary or azimuthal quantum number. As a matter of fact, for our curriculum here, we are going to use the azimuthal or subsidiary quantum number. All right? So that is, we are going to explain it in details in our next class so that you will understand that very clearly and you see how to apply them. And you now learn to write electronic configurations. You'll be able to write, you can see that, you'll be able to write electronic configurations of different atoms